We're now going to look at partial fraction decomposition. So this is where we're taking a complicated fraction and trying to rewrite it as a sum or difference of simpler fractions. And so the first thing that we want to do when we're doing these is we want to look at the degree of the numerator and the degree of the denominator. If the degree of the denominator is larger, then we're just going to jump in and do partial fraction decomposition on it. If the degree of the numerator is larger or the same, then the first thing that we have to do is long division of polynomials. And then we're just going to look at the remainder over the divisor and try to break that down as a sum of simpler fractions. When you're dealing with these, the first thing you want to do, after you look at the degree of the numerator denominator, when we're approaching to do this partial fraction decomposition, the first thing you want to do is factor the denominator as far as possible. So recall when we were working with polynomials and we were finding those zeros of the polynomial, how we broke up a polynomial as a product of factors, of linear factors. And if the quadratic factor was not reducible over the real numbers, we kept it as a quadratic. So same sort of idea here when we are factoring this denominator. So I'm going to pull an example, and then I'm going to show you the steps of how to approach this. And then I'll give you some more guidelines on what we need to do depending on what the factor in the denominator looks like. So let's pull an example. Okay, so our example in front of us is 3x all over x plus 2 times x minus 4. And we want to rewrite this as a sum of simpler fractions. If I look at the degree of the numerator, if you look at the degree of the numerator, that's degree 1. And if we look at the degree of the denominator, if we multiplied out those factors, that's degree 2. So we're going to jump in and do our partial fraction decomposition. So the denominator is already factored for us, and we have to look at what type of factor we have. Is the factor linear? X plus 2 is linear, x minus 4 is linear. So we have two linear factors. And then once you look at the factor, is it linear or quadratic and not reducible over the reals? Does it repeat itself? Does that factor have multiplicity? Well, x plus 2 only occurs there in the denominator once, and x minus 4 occurs there in the denominator once. And so what we want to do, if the factor only appears once and is linear in the denominator, we're going to break this down as A, capital A, all over one of our factors in the denominator. So how about x plus 2? Plus, and now we're going to go to capital B all over the next linear factor in the denominator. So x minus 4. If there were more linear factors, I would continue on in this manner until I've gotten through all the factors in the denominator. I will go over what to do if they're quadratic or repeating later in a different example. But this is what we're going to be doing if they're linear and not repeating. So once we've rewritten it like this, we want to clear your fractions, and we're going to clear the fractions each time by multiplying through by your denominator that we started with, that x plus 2 times x minus 4, and that will clear our fractions. So clear fractions. Our LCD, we can see is x plus 2 all times x minus 4. So I'm going to multiply that on both sides of my equation. So when I multiply it on the left-hand side, we're just left with our numerator, 3x is equal to, well, when we distribute this to the first term or fraction on the right-hand side, notice that x plus 2 cancels. So we're left with A all times the other factor, x minus 4, plus B, and then we're distributing, so x minus 4 cancels, and we're just left with the x plus 2. Okay, so once we've cleared the fraction, now we're going to distribute our capital letters inside those parentheses. So we have 3x is equal to capital AX minus 4a plus, now distributing the b, we have bx plus 2b. Okay, so now we want to match the coefficients on the left with the coefficients on the right. So coefficients in front of the like terms. On the left equal to those on the right. Okay, so notice that we only have a 3x on the left-hand side. So the coefficient in front of the x is 3. So let's look at all the terms on the right-hand side that have an x in it. So we have this ax here and we have this bx here. So the coefficient in front of the 3x, that's the 3. This is equal to the coefficients in front of the x on the other side. So we would have a plus b. So if we add ax plus bx, it better give us back 3x. Excuse me. Okay, so now let's go to the constant, because I have a couple of terms on the right-hand side that don't have any x's on there. And so if I think about what is the constant on the left-hand side, we can think of it as 0. We can think of this as 0 plus 3x or 3x plus 0. So the constant on this side is 0. This is equal to the coefficients in front of our capital letters A and B. So this would be -4 plus, negative 4a plus 2b. If we sum those together, sorry, not if we sum those, yeah, if we sum -4a plus 2b, we must get back the constant 0. So now we have a system of equations. So we want to solve this system of equations. And so it's your choice what method you want to go about this. I notice if we use the elimination method, so we can multiply maybe 4 by that first on the first equation. And when we sum it to the second equation, then that would get rid of our A and we could solve for B. So let's do 4 times, I'm just going to call it row 1. So 4 times row 1, so 4 times 3 is 12, is equal to 4 times A, so 4A, plus 4 times B, 4B. So if I sum these two together, I get 12 is equal to 6B. So now I know what my B is. I can divide both sides by 6 and I get B is equal to 2. And if I know what B is, I can go back and do back substitution and figure out what A is. So if I go back here and this first equation, that 3 is equal to A plus B, 3 is equal to A plus 2, A must equal 1. And we pretty much now have it. So our fraction we started with, this 3x all over x plus 2 times x minus 4. This is equal to A. Well, we found what A was. It was 1 all over x plus 2 plus b, but we found b was 2. So 2 all over x minus 4. And so we just rewrote a single fraction and a sum of simpler fractions. Okay, so the next example is x squared all over x minus 1 quantity squared, all times x plus 1. So x minus 1, that's a linear factor. X plus 1 is a linear factor, but the factor x minus 1 quantity squared, that x minus 1 is appearing in the denominator more than once. And so if you have a linear factor appear more than once, this is how you're going to rewrite it. You're going to do kind of similar to what we had done before, that capital A all over x minus 1. And now we're going to do plus b all over x minus 1 quantity squared. And so you're going to continue to do this for the number of factors that you have in the denominator. So if this was to the 5th power, I'm going to change it back, but let's just say that this was to the 5th power. If that was to the 5th power, I would continue to go on here, c all over x minus 1 quantity cube plus d all over x minus 1 to the 4th plus e all over x minus 1 to the 5th. Okay, so I'm going to do that until I get up to the number of factors that are in the denominator. In our case, I'm going to change it back so things work out nicely. In our case, we just had to the square. So now looking at it, we have another factor down there in the denominator, which is x plus 1. So I'm going to write a fraction, c all over x plus 1. Okay, so next step is to clear your fractions. And we can do that by multiplying through by our LCD. And our LCD in here is x minus 1 quantity squared, all times x plus 1. Okay, so multiplying both sides of our equation by that. When we multiply it on the left-hand side, the whole denominator clears and we're just left with an x squared term. This is equal to, so distribute it to each fraction, the LCD, on the right-hand side. And when we do that, we would get this is equal to a all times, well, one of the x minus 1s cancels and we're left with 1 x minus 1, and we're left with the x plus 1. Plus b, distributing this, x minus 1 quantity squared cancels, so all we're left with is x plus 1. Distributing it to the last fraction, we're left with plus c, the x plus 1 cancels, and we're just left with the x minus 1 quantity squared. So we want to clean this up and distribute things out on the right-hand side. And then we're going to match the coefficients with like terms on the left equal to the ones on the right. Okay, so we have x squared here is equal to a all times, well, x minus 1 times x plus 1, that's a difference of squares. That's the same thing as x squared minus 1. Plus, let's distribute that b. So we have bx plus 1, 1b, plus c. If I distributed it out, x minus 1 times x minus 1, and combine like terms, this is x squared minus 2x plus 1. So we're almost there. Distribute the a. We get x squared is equal to ax squared minus a plus bx plus b plus cx squared minus 2cx plus c. Okay, so we're going to all the coefficients in front of the x squared. That's the highest degree term I have. And so the coefficient in front of the x squared on the left-hand side is 1. This is equal to, so I'm looking at the coefficients, summing the coefficients in front of x squared on the right-hand side. So that would be a plus c. Notice that there's no 0x term here. So we can think of this as in here plus 0x. So now let's go in and let's look at all the coefficients in front of x on the right-hand side. So 0 is equal to b minus 2c. And the last one is our constant. Our constant on the left-hand side is 0. So we can think of that as 0 plus if you wanted. So on the right-hand side, we have negative a plus b plus c. Okay, so it's up to you at this point to determine which way that you want to solve this system. I may ask you to solve the system using matrices, and it's a great tool right here, right now. So let's look at it, and it would be a good review. So I'm going to rewrite my matrix. So I have my coefficients of A, B, C, and then my augmented matrix equals the constant on the other side. So my coefficient for my first equation are 1, there's no B, 0, C is 1, equals 1. So for my second equation, there's no A, so I'm going to put a 0 there. B is 1, in front of C is negative 2, is equal to 0. And then for my third row, I have negative 1, 1, 1, and 0. Okay, so working with this matrix, we're going column to column, working left to right, get the one where we need it, the ones where we need it in that main diagonal already. And I can see that if we add row 1 plus row 3, we would get this to be a 0 where we want it down in here. So let's do row. Let's maybe go over here. So we're going to do row 1 plus row 3. I'm going to rewrite my row 1, 1, 0, 1, 1. Rewrite my row 2, 0, 1, negative 2, 0, because I wasn't really changing those. And now let's rewrite our new row 3. So row 1 plus row 3. 1 minus 1 gives us 0. 0 plus 1 gives us 1. 1 plus 1 gives us 2. And 1 plus 0 gives us 1. So our column 1 is done. Let's move to column 2. Column 2, we have the one where we want it. Now we just want a 0 above, which is there, and a 0 below. So I can get a 0 below if we do negative row 2 plus row 3. Okay, but row 1 and row 2 are staying the same. So let's first rewrite that 1, 0, 1, 1, and 0, 1, negative 2, 0. Our new row 3. So 1 plus 0 is 0. Oops, sorry. First of all, 1 plus 0 is not 0. Oh my goodness. Negative row 2. So negative 0 plus 0 is 0. Negative 1 plus 1 is 0. A negative times a negative 2, that's 2 plus 2, that gives us 4. And then we have 0 plus 1 is 1. So at this point, I noticed that we can look at the row 3 and we can tell what C is. So if we rewrote row C as an equation, right, this is saying that 0x plus 0, not x, 0a plus 0b plus 4c. So 4c is equal to 1. So from here, we can tell what C is then. C has to be 1/4. We can go back in and plug in what C is into equation 2. So our equation 2, or row 2, if we read that off from this last matrix we have 0a plus 1b, so b, minus 2c equals 0. But we know what C is above, so we can do our back substitution in here. So if we did back substitution, we have b minus 2 times c. C is 1/4 equals 0. So b minus 1/2 equals 0. So b is equal to 1/2. And then for our row 1, reading that off, we have 1a plus c equals 1. Well, we know what C is. It's 1/4. So we have A plus 1/4 is equal to 1. Excuse me. So let's subtract 1/4 on both sides. So we get A is equal to, well, 4/4 minus 1/4 is 3/4. Okay, so back here, we now know what A, B, and C are. I don't really want to have a fraction in the numerator over the denominator. I don't want a complex fraction. So when I write this, we can think of this as, right, this is the same thing as A all times 1 over x minus 1. So maybe think of it that way. So our A value in our case was 3/4. So from here, our original x squared all over x minus 1 quantity squared times x plus 1 in that denominator. This is equal to our A value, which is 3/4 times 1 over x minus 1 plus our B value. B was 1/2. So plus 1/2 times 1 over x minus 1 quantity squared plus C. C was 1/4 times 1 over x plus 1. I'm going to clean it up a little bit. This is the same thing as 3 all over 4 times x minus 1 plus 1 all over 2 times x minus 1 quantity squared plus 1 all over 4 times x plus 1. So we just solved that complex, or sorry, we just rewrote that complex rational fraction as a sum of simpler fractions. Okay, so we looked at the case, what we do if it's just a linear factor, not repeating. We looked at cases where it was a linear factor and repeating. And now we want to see what do we do if it's a quadratic factor that's not reducible over the real numbers. So let me pull another example. So our next example is 1 all over x plus 1 times the quantity x squared plus 4. That x squared plus 4 is not reducible over the reals. If I had solved for x there, I would get plus or minus 2i. Okay, so we want to rewrite this. That factor x plus 1 is only appearing once. And so we would write that as a all over the x plus 1. If it is a quadratic in the denominator, then what we want to do is we want to sum it where we have a linear function in the numerator. And so we're going to write that as, how about cx plus d all over the x squared plus 4. If this was repeating, then I would continue to do that and sum up that number of fractions, the number of times it's repeating, where that factor is increasing by 1 degree each time. Okay, but it's not. So let's keep it like that. Same process, we're going to clear our fractions. So if we multiply through by our LCD, we're multiplying both sides by x plus 1, all times x squared plus 4. So on the left-hand side, we're just left with 1 is equal to a all times the factor x squared plus 4 plus the cx plus d all times the factor x plus 1. So that's what we're left when we multiply through by the least common denominator on both sides of our equation. So let's distribute on the one side. So we have 1 is equal to ax squared plus 4a plus, so distributing, we have a cx squared plus a cx plus a dx plus a d. Okay, so let's now write our equations for our system. And so notice there's no x squared term in here. And so we can think of it as 0x squared on the left-hand side. And so 0 is equal to the terms with x squared on the right-hand side, just the coefficient a plus c. Now let's look at the terms with just an x. Well, there's no term with x on the left-hand side. Thinking of that as 0x, the coefficient in front is 0, is equal to coefficients on the right in front of x are c and d, so c plus d. And now looking at our constant on the left, that's 1. This is equal to the constants on the right, 4a plus d. Okay. So let's make this as a matrix. So we have A, which is 1. B is 0, C is 1, D is 0, line, and then 0. Our second equation, we have A is 0, B is 0, C is 1, D is 1, equals 0. And the last one, we have 4, 0, 0, 1, 1. Let's get rid of that 4 in the denominator. Not in the denominator, the 4 in the last row. And we can do that by -4 row 1 plus row 3. So row 1's the same, 1, 0, 1, 0, 0. Row 2's the same, 0, 0, 1, 1, 0. And the next one we have -4 times plus -4 times 1 is -4 plus 4 is 0. -4 times 0, 0 plus 0 is 0. -4 plus 1 is -4. -4 plus 0 is -4. -4 times 0 is 0 plus 1 is 1. And then lastly, -4 times 0 is 0 plus 1 is 1. Okay, so let's look at this. We have a row of all zeros there. My guess is that B is equal to 0. Hey, we don't have any B. That's my problem. I'm like, what the heck? Excuse me, we don't have any B. I could have wrote that as BX plus C, but I didn't. I was wondering why we had more variables than equations. So let me get rid of this row because that technically is not there. And we're in the form of A, C, D. Okay, so let's look at our column 2. That 1 is what we want. And we're going to use that 1 in the row 2 to get the 1 above and the -4 below to be a 0. So let's do negative row 2 plus row 1. Row 2 is the same, 0, 1, 1, 0. Okay, so 0 plus 1 is 1. -1 plus 1 is 0. -1 plus 0 is -1. 0 plus 0 is 0. Now let's do 4 times row 2 plus row 3. 4 times 0 is 0 plus 0 is 0. 4 times 1 is 4 minus 4 is 0. 4 times 1 is 4 plus 1 is 5. 4 times 0 is 0 plus 1 is 1. So again, this is where I would do back substitution. So I don't have to deal with fractions. So I get that 5D is equal to 1. So D is 1/5. Plugging it into the second equation. The second equation was, I have to remember I don't have a B, C plus D equals 0. So C plus 1/5 equals 0. So C is equal to -1/5. And the first row says that A minus D equals 0. Well, D is 1/5. So A minus 1/5 equals 0. So A has to be 1/5. Okay, so where did it go? Where do we start? It was right here. So right now we have A. A is 1/5, right? All times 1 over x plus 1. Plus, I'm going to write fractions in the numerator right now. So 1/5 is -1/5. X plus D, and D is 1/5. All over that x squared plus 4. So this is the same thing as 1 over 5 times x plus 1. If we factored out a -1/5 here, that would be times x minus 1 on the numerator. So let's pull out a -1/5 all times x minus 1 all over x squared plus 4. Just going to clean it up a little more. So 1 over 5 times x plus 1 minus x minus 1 all over 5 times the quantity x squared plus 4. So what we started with gives us back this. Okay, so I want to look at one more type where we have a quadratic and the quadratic factor is repeating in the denominator. Okay, so looking at the next example, x cubed plus 1, all divided by x squared plus 16. That x squared plus 16 is quantity squared. So x squared plus 16, again, is irreducible over the real numbers. And so I notice that it's a quadratic, but that quadratic is repeating. It's repeating twice. And so when I rewrite the fractions, we're going to have ax plus b all over one of the factors, x squared plus 16, plus cx plus d all over, now we're going to x squared plus 16 quantity squared. And we would continue to do that, raising the degree of that factor by 1 until we got to how many factors we have, which is 2 of them. So we stop. Our LCD, we can multiply both sides of the equation by this x squared plus 16 quantity squared. And so on the left-hand side, we're left with x cubed plus 1 is equal to ax plus b, put that in parentheses because it's more than one term, all times only one of the x squared plus 16s cancel, so we're left with one of them. So all times x squared plus 16 plus cx plus d, and everything cancels when we distribute it. So expand the right-hand side by distributing. So we have x cubed plus 1 equals, so this is going to be an ax cubed plus a 16ax plus a bx squared plus a 16b. And then we have cx plus d. So coefficient in front of the cube is 1. Coefficient in front of the cube on the right-hand side is just a. So we actually know what a is right away. A is 1. Coefficient in front of the x squared is 0. And so 0 has to equal the sum of the b's over here. I'm sorry, of the terms with the x squared over here. So that's just b here. So b is 0. Notice there's no x term either. So our x term is 0. And terms in front of the just x are 16a plus c. And then our constant is 1, is equal to, so one's with just the constant. So that's 16b plus d. Okay, we can just do direct substitution right away. We know that a is 1. So that third equation we have 0 equals 16 plus c. So c is negative 16. If we go back in and we plug that in, or plug in 0 for b into the fourth equation, we get that 16 times 0, 0 plus d is d. D is equal to 1. Okay, so we know A, B, C, and D. So going back up into here, let's just rewrite what A, B, C, and D are in there. So this is equal to A, which we said was 1. So 1x plus B, which is 0. So x plus 0, we can just leave it as x, all over x squared plus 16, plus C. So that's a negative 16x plus D, which is 1, plus 1, all over x squared plus 16 quantity squared. Okay, so we've looked at every single case where we've had a linear factor non-repeating, linear factor repeating, quadratic factor irreducible over the real numbers, not repeating, and then repeating. We have not looked at the case where our numerator is the same degree or larger than our denominator. So let's look at one of those cases, and then we're done with this section and we'll take a break. So let me just pull one of those out first. Okay, so here's an example where we have an improper fraction where the degree of our numerator is larger than the degree of our denominator. So if that was the case, we did not start with partial fraction decomposition. We first needed to do long division. So we want to divide x squared minus 4 into this 5x cubed. I'm just going to put a placeholder. I might not need it. 0x squared plus 2x minus 1. So we look at our first term in our divisor, which is x squared, and we think to ourselves, x squared times what would give us 5x cubed? Well, that's just 5x. So let's put 5x here in our quotient, and we're distributing that 5x to each term in our divisor. So doing that, we have 5x times x squared is 5x cubed, minus 5x times 4, so minus 20x. So I actually didn't need that placeholder, minus 20x. And remember, we subtract this off. So changing the sign, we have 5x cubed minus 5x cubed, those cancel. 0x squared minus 0x squared or plus 0x squared, there's nothing there. And here we have a 2x, this is really minus a negative, so plus 20x. This is 22x. Bringing down our next term, minus 1. Notice that this is less than the degree of our divisor. So that we're done. That is our remainder. So this is equal to the quotient, which is 5x, plus the remainder, 22x minus 1, all over the denominator, x squared minus 4. So when we do partial fraction decomposition, we're only doing the partial fraction decomposition on that fraction, that remainder over the divisor. When we rewrite out our answer, don't forget about this 5x plus in front of it. I'm going to rewrite that one piece with factoring the denominator. X squared minus 4 is not a quadratic. That's irreducible. It is reducible over the reals. So there's 22x minus 1 all over, well, x squared minus 4, difference of squared, could be rewritten as x minus 2 times x plus 2. So this is equal to a over one of the factors, x minus 2, plus b all over one of the other factors, x plus 2. It really doesn't matter which one I could have put a over x plus 2 and b over x minus 2. In the end, we would get the same result. If we cleared our fraction and multiplied both sides by that LCD, then we're left with 22x minus 1 is equal to a all times x plus 2 plus b all times x minus 2. So distributing on the right-hand side, so left-hand side, we have 22x minus 1 equals ax plus 2a plus bx minus 2b so we have 22 is equal to a plus b. And we have -1 is equal to 2a minus 2b. I would probably do the addition method here, or elimination method. Let's multiply that first row by 2. So 2 times row 1, that would give me 2 times 22 is 44, is equal to 2 times a is 2a plus 2 times b is 2b. If I sum these two equations right here, -1 plus 44, that is 43, is equal to 2a plus 2a is 4a. So I get a is 43 over 4. Not pretty, but it's not bad. I mean, we can do it. And then let's plug that back in, maybe to the first equation. So we have 22 equals a, which is 43 over 4 plus b. I'm going to multiply this by 4 over 4. So when I subtract, I have 88 fourths minus a 43 fourths is equal to b. So b must be 45 fourths. Okay, so our original equation, we get 5x plus, the remainder piece. The remainder piece was a, which is 43 over 4, times, and that 4 is times x minus 2, plus b, which is 45 all over 4 times the x plus 2. So our original can be simplified after doing long division and partial fraction decomposition over the on the remainder divided by the divisor. Okay, so this is a great place to stop unless there's some questions. And if there's questions, I'll come back and address those.